Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so let's talk about CrowdCam. We are done with the restricted setup, no more calibration. After this to work, I told my advisor I don't want to do any more calibration in my PhD. So we moved to talk about CrowdCam. So you probably got to see this setup. Many people holding mobile phones and capturing some highlights of a dynamic event. And we are interested in analyzing the dynamic content using this set of still images. Now, there are methods that looked on this setup, but they usually try to analyze the static regions of the scene, for example, phototourism. And we are interested in understanding the dynamic information we have from this data. So let's assume we have 15 images in this case, taken from different locations and different time steps. If I would ask you, what is the first image? What is the last image? It would be very hard to say. Let's look at the image in a random order. So you can see the viewpoint is changing, the time is changing. There is rich temporal information in these images, but it's very hard to analyze it just visualizing the images in a random order. So here you can see the images ordered in the correct order as we computed in our method. So what we are interested in is doing the first step toward analyzing dynamic from still images. And the problem we were addressing is photo sequencing. So we're given with n images, and we want to determine the temporal order between them. So if we are given with n images, we have n factor possible permutations. We have several assumptions. First, we assume that the images are taken within short time interval. The extension to longer time intervals can be done by using the imprecise clocks of the cameras. And we assume the two images were taken approximately from the same position. And this is a reasonable assumption because people often take many pictures and they don't tend to move much while they capture the images. And we treat one of them, we choose one of them to be the reference image. A preliminary step of our method is to detect features and match them to the reference. Then we classify them into static features and dynamic features. The static features provide us with the geometry, and the dynamic features give us the temporal information. So let's see what we do with that. Here you can just see an example of how the dynamic feature looks on the images. And you can see that, for example, not all features are found on all objects. So here you can see that on this boat we found features, but here we don't have these corresponding features. Here again, the green boat is detected here, but we don't have any matching feature here. So the outline of our algorithm, as I said, consists of extracting the static and dynamic features. We then, every set of corresponding dynamic features in subset of the images give us a partial order of the image it was found in. And these partial orders are not necessarily consistent. They could be errors due to matching, wrong geometry, or that kind of stuff. And what we want to do is to take all these partial orders and to output one full consensus order that will agree as much as possible with all these partial orders. So first, I will talk about this part, how each set of corresponding feature, how we compute the partial order. And this is done using geometry. And the second part, I will talk about how we do this aggregation. And we use something that I hope will be useful for other things in computer vision, rank aggregation. It was used to rank web pages. And we treat each of these partial order as a voting. So we'll talk about this part later. Let me start from, yes?
So are you assuming that basically an interest point, when it is sort of detected, then it can only sort of, it will never disappear, right? Because it might happen that the interest point, that the boat comes in,
Yes.
and then goes away.
Yeah, I will talk about the motion assumption in a minute. We assume that inside this small interval, time interval, the motion is approximately linear. So yeah, we don't account for changes in the direction. And it doesn't have to be exactly linear, but approximately. So let's assume we have a 3D point that moves on a straight line. For simplicity, let's assume it's exactly a straight line. And it is sampled in different time steps by different cameras. So of course, if we had a 3D location along the line, we could say that the order of points, the spatial order of points along the line equals to the temporal order. But this requires estimating the 3D points or estimating the 3D line. Now, there are methods that can compute the 3D line, for example, using 5 views and using full calibration. But I already said I won't do full calibration, so we didn't estimate the 3D line. And we want to avoid the 3D reconstruction. We want to compute the order without recovering the 3D. Alternatively, if we had the projection of all points into one of the views, so here again, if we had the spatial order on the image plane, it will be equal to the temporal order. So what we do is mapping to one of the images, mapping all dynamic points to the same reference image. So for example, if we have 2 images and I1 would be the reference, we have the projection of a 3D point at time t1 to image I1. And I assume that we have the same location approximately at different time steps. So I have also one more projection at time t2. This will give us the projection of the 3D line onto the image plane. Now, if I have another corresponding image in IK, I can compute its projection to I1 by taking the intersection between the epipolar line and the motion line. And this will give us the mapping to the reference image. Now, it's very important to note that we don't care about the exact location of the points on the image plane. All we care is the relative order. Okay, so I don't care if it's not really a straight line, and I don't care where it's exactly intersect the epipolar line. All I care about is that this point will not change their order along the line. So this way we take each set of corresponding dynamic feature and map it to the reference view, and we have a partial order computed by looking at this spatial order on the image plane. Yes?
How do you resolve this two-fold ambiguity?
Excuse me?
The images are sorted in forward time and not in the reverse order.
I'm sorry?
I mean, when you have those images, you have 2 possible explanations that are equally likely, I guess.
Yeah, I'm sorry. Yes, I assume that from the same camera I have 2 images. The 2 images that I assume that are taken from approximately the same time, at the same location, these 2 points. Yeah, I assume that I have 2 points that are from the same camera, approximately from the same position, and they give us the relative, the direction. Because there are images that are taken from the same camera, you can assume that you have the order between them. So we assume we have the direction. Now, let's look at a graph representation of the problem. So we treat the images as nodes of the graph. And let's assume we detected this set of corresponding dynamic features. In this case, it's a full order. It determines a full order because it was detected in all 5 images. And we can represent this order by putting an edge between image I to image A if image I comes before image A. Another example, we can have also partial order. In this example, the partial orders, the green one, agrees with the red one. But it's not always the case, and we can also have conflict when we have, for example, a wrong partial order. And also, we can, here I only draw the direct edges. We can also infer edges between pairs using transitivity. So for example, here I can add these edges and these and this. So now what is the problem? Given this representation, I have possibly conflicting partial orders, and what I want to do is to compute the most consensus order using this information. And this problem now is known as rank aggregation. It was used mostly on web applications when they try to rank web pages. And in general, you can see here the objective function. This is the Kendall distance to who knows, who's not. The objective function wants to find the order sigma optimal, which will minimize the disagreement, the pairwise disagreement between all partial pairs. And in general, this problem is NP-hard. So we use the Markov chain approximation, and I will explain the intuition behind it. So now each image is a state in the Markov chain, and an edge between state I and state J is the probability that that image I was captured before image J. And we compute these weights from the partial orders we already computed. Now let's assume that we have partial orders that are all agree with each other. So in this case, this graph would be a DAG. We won't have any cycles. And let's consider a random walk on this graph. So we start with the initial state is chosen according to a uniform distribution. The probability to be in each of the states is equal. What will happen in the steady state? We will get stuck in the sink. Yeah. So we will get stuck in the sink after getting to the steady state. And then we can say that the sink is the last frame, the last captured image. We can remove it and repeat. In this case, that the graph does not contain cycles, we can, instead of doing what I showed right now, we can just use a topological sort and solve it in a polynomial time. But in practice, we do have cycles. The graph can contain cycles. So what happens in this case is that if we start from a uniform distribution, we will end, the distribution will be distributed on the sink component in this case. So this is a heuristic part of the algorithm. We take the last image to be the image with the highest probability, remove it, and repeat. In practice, we define the transitivity matrix where the component ij is the probability that I came before j. And we start from a uniform distribution. The next state will be just multiplying m by this vector. And in the steady state, we get to finding these eigent values of the matrix. So in practice, we run power iteration in order to find the eigen values of this matrix. And that's how we get the full order. So some results. Here you can see 9 still images captured from different viewpoints, different time steps. These were the 2 reference images. And here you can see the images in a random order. And in order to validate the results, what we did, we aligned the images according to the static features to the reference image. So this is the results as computed by our method. Here again, another scenario. Here you can see, validate the results according to the girl location along the slide. This was the beach, Tel Aviv. So if I conclude, what we wanted to show in this work is that CrowdCam can be used to analyze the dynamic content of the scene, not just the static. We introduced the photo sequencing problem, which is a novel problem, and we offered a geometry-based solution. We used rank aggregation that I believe that can be useful for other computer vision problems. And future works include relaxing the assumptions, doing better photo sequencing, extending computer vision tasks to set of still images, and investigating the theoretical part of space-time equivalence. Thank you.
So we have time for questions.
I have two comments. Actually, one comment, one question. So your initial images about the CrowdCam are slightly misleading because there you don't have the mostly static background. So this, I think, making whatever work on that.
Which image?
I mean, what you had in the kind of teaser image when you introduced the CrowdCam.
There
were all these people with the...
yes.
So, but in this work you assume mostly a static background, I have the impression.
But in the first images, I didn't show you the 3D scene, so you don't
know
the static...
But then, so this work, do you know the work by Grant Schindler?
Yes.
Because, so...
But this was about the building aging, that work?
I mean, the two papers that, in some sense, the programmer related, and it all was about urban scenes. But especially his first work, I think, is in a method relatively close to what you propose by considering appearance and disappearance of certain features and to use this as a hint to sort images. Because what you assume, and you could also use this here when you have your feature tracks, so what you would think is when you track features, you want to align the images in a way temporally such that you have as long feature tracks as possible. You don't believe that you are flipping always. If you detect features in one frame, in the next frame you don't. This is not happening. So I think in that sense it's quite related. Can you comment maybe on some difference or?
Yeah, so first of all, I think that this work was about much more longer time intervals. Here, you take a very short time interval, and you don't have to have the correspondence, of course, in all images. It's enough to have very few correspondences in very few images, and then the extension to longer time would be just combining this.
So the construction and deconstruction of a building, if you compress the time scale, you're somehow similar. Then the person moving or walking through a scene.
I don't know the exact detail of this work, so it's hard for me to tell you if it's the same or not. But
no, it's not the same. But it's the program. I think it's very related.
Okay.
It does sound interestingly, qualitatively, it's quite a different approach, but it would be nice to compare them.
You get a measure of temporal distance between two images just by how many corresponding points you get.
I don't think it's a good measure because, as I said, you can have very few dynamic points that you find correspondence. These images are very hard to match. I tried several methods, and this would be, I guess, another work to do good matching between these kind of images. But the viewpoints are very different, and the objects are moving non-rigidly, so it's very hard to have long tracks in these scenarios.
Does it fail a lot?
What?
Does it fail a lot? I mean, do you have to try many examples to get something that works?
No, we didn't, but it's supposed to comply with our assumptions. Also, there are more results in the paper when you can see that in practice the motion can significantly deviate from linear motion. You can handle some movement between the reference camera at the 2 time step because what I said, because all you care about is really performing the order and not precise, accurate results. And what we are depending on is the matching. If we will have a better matching, I think that we can also get better results. But now we are working on relaxing the assumption, replacing them in some more practical assumption that we can use for real applications. So this is just the first step, and we hope that it will open the door to other application using this CrowdCam or group photography.
Okay. Are there any other questions? Okay, let's thank Ali again.
Thank you.